negative as well. And the way to do that is to look at the two factors separately. We draw a sign diagram for x minus 3/4. Starting with negative numbers, this factor is negative up to x equals 3/4. For x greater than 3/4, the expression is positive. For the other factor, x plus 3/4, it's negative up to minus 3/4, and it's positive after. Forming a product, we only get negative values between minus 3/4 and 3/4. So, the values of x satisfying this inequality lie in this interval. Well, that's the solution to this inequality. But we want values of x which satisfy this inequality as well. Now, this inequality means that this minus this is positive. So 3x squared plus 5/16 must be positive. So look at x squared. That's always positive or 0, and so is 3x squared. And we add on 5/16. So this whole expression is always positive for every value of x. So this inequality is always true. And this one's true between minus 3/4 and plus 3/4. So the interval we want, where the original inequality holds, is the intersection of these two. And that's just it.
What Bob did was to take the derived function of the iteration function and find those values of x to which the derived function has modulus less than 1. And he found that when x lies between minus 3/4 and 3/4, then the modulus of the derived function is indeed less than 1. So, if you take any point in this interval, the tangent at the corresponding point on the curve has slope of modulus less than 1. Now, there's another important fact about this interval for our purposes. We know it contains a solution to our equation. Well, that looks clear enough from the diagram. So we could check this by calculating the value of the function at each endpoint. That would tell us that the curve lies below the line y projects at this end, but it lies above the line at this end. And so we would know that the curve must cross the line somewhere in between. Now, this all means that the interval contains a solution of the equation. And if we start an iteration with a point in this interval, then the next term must be closer to the solution. We've seen two iterations already. Starting from point 6, we got something which converged. And of course, point 6 is in this interval. Starting from 1, which is outside the interval, we got something which diverged. Now, what about minus a half? Well, that's in the interval. Now, does that mean that the iteration will converge? What do you think?
Well, that's a bit embarrassing. It's not converged. Well, why not? We started in the interval, so we should have got closer to alpha. But x2 is outside the interval. And x3 is even further away. And we get a staircase away from the solution. Well, how did we manage to jump outside the interval? Starting in this interval guarantees that x2 is closer to alpha than x1. And so it is. Alpha is here, and x2 is closer than x1. The problem is that x1 starts so far away from alpha that when it jumps over, it gets outside the interval. There's not enough room on this side of alpha to be sure of getting into the interval. So x3 needn't be closer to alpha than x2. In fact, it moves further away, and we get a divergence system. So our condition mod of f prime of x is less than 1 is an important condition. But on its own, it won't guarantee convergence. If we start too far away from alpha, we could jump over alpha and end up outside the interval. So we need a second condition. We must start our iteration near enough to alpha to make sure we can't jump over alpha and end up outside the interval. So, how can we be sure that we're starting near enough to alpha? The trouble is that we don't know the value of alpha. What we do know is that alpha lies in this big interval. This interval is too big. We don't need a smaller interval containing alpha. Well, how about that then? We can check that it contains alpha by showing that the curve is above the line at this end and below at the other end. If we start with x1 in this interval, are we near enough to alpha? Well, what's the furthest that x1 could be from alpha? It's got to be the length of this interval. Alpha might be at this end, and we might start at the other. We must make sure that if we jump over alpha, we don't go outside the big interval. And that'll be okay if we have an equal amount of space on the other side of alpha. On the other hand, alpha might be at this end, and we might start at the other. So we need the same amount of room on the other side. So we need a small interval containing alpha, which has an equal amount of elbow room on either side within the big interval. If we start inside an interval like that, we're bound to get convergence. So now we have two conditions to check for guarantee of convergence. The first condition is essentially a check on the function itself. The second condition is a check on the starting point. Between them, these two conditions will guarantee us a convergent system. So let's finish by going back to our problem from the start of the program. Can I set a starting value if I can guarantee convergence? Now I know that the first condition is satisfied between minus 3/4 and 3/4. And from the graph, I can see also that I have a solution somewhere around here, between about 0.5 and 0.6. So let's test to see if any starting value in this interval will give me a convergent system. Do I have enough elbow room on either side? Well, certainly there's enough elbow room on this side, and the distance from here to here is 0.15, which is longer than the length of that interval. So there's enough elbow room on that side as well. So that confirms what we saw at the beginning of the program, when we used 0.6 as the starting value, and we got a convergent system. Now here's a question for you, and one that you should be able to answer. What will happen if I start iteration with a starting value of 0.5?
The next program for this course can be seen in 2 weeks' time after Easter. Area for revision shows how the area underneath the hyperbolic graph is related to the natural logarithm function. That's on Saturday the 25th of April at 7 is on BBC 2. And on 2 at the moment, the Modelling by Mathematics course is looking at rates of change. While here on 1, on Data Collect, the course on data models and databases will discover why it's useful to keep data about data. This is BBC One, with programs for the Open University. In a minute or so, the Enlightenment course will be exploring Edward Gibbon's motives for writing his masterpiece, The Decline and Fall of the Roman Empire. First though, a little music. We continue this morning's Open University programme here on One Now as the Enlightenment series explores Edward Gibbon's message from his epic work, The Decline and Fall of the Roman Empire, in Gibbon and the Ruins of Rome.